I went early for like almost like 5 minutes early.
Okay.
For a doctor appointment.
No problem.
Yeah.
Okay. Okay, friends, we are on page 52, page 52. Now, on pages, let's see, 52, 53, 54, they're all enriched. So if you're like, oh, I don't want to learn enriched stuff for 3 pages, you could, if you wanted to, do some of the weekend's homework, which is going to be 3.4b, which is a review of matter and particles and bonding. Okay? So 3.4b, if you're like, I don't want to do the enriched stuff. B, and that is pages 75 to 80, I think. 75 to 80? Yeah. Okay. And the other thing that I would like you to do over the weekend is make yourself study notes because your test is next Wednesday. Okay? All right. And in the meantime, going back here. Okay. So now we have talked about this in the past, but here we're going to really focus in on it. So the strength of an electrostatic attraction depends on the amount of charge. As the amount of charge gets... Oh, actually, this is a good question. If the strength of the electrostatic attraction depends on the amount of charge, who is the independent variable and who is the dependent variable? We've got our choices: strength and amount of charge. Who is the independent variable and who is the dependent variable? Yeah? Sorry? The strength is so the strength depends on the amount of charge. So strength is the dependent because it depends on the other thing. And the independent is the amount of charge. And if we were to graph this, if we did a little graph of, where have I got room to draw a graph? Maybe over here. Maybe over here. Over here looks good. So strength goes on my y-axis because it's dependent, and amount of charge goes on the x-axis because it is independent. As the amount of charge gets bigger, what happens to the strength of the electrostatic attraction? As we have more, like if I had a 1 plus charge as opposed to a 2 plus charge, which one would have a stronger force associated with it? 1 plus or 2 plus? 2 plus, okay? So as the charge gets bigger, the strength gets bigger. Is that going to have an uphill slope or a downhill slope? That's going to have an uphill slope. And is that a positive correlation or a negative correlation? That is a positive correlation. Is that a direct or an inverse relation? That is a direct relation. Okay, and so that's what the charge graph looks like. And so that's why when we have only a single bond right in the middle here, we have a 2 negative charge. Each of those little electrons has a negative. If we have a double bond, we got 1, 2, 3, 4 negatives. And then I haven't put it here, but if you had 6 negative charges between the nuclei, it would be even more. Okay, so this is a weaker electrostatic attraction. And if you're tired of writing electrostatic attraction, you can just write ESA. That's not like a common abbreviation, but we're going to use it because I know it's tiring writing things. And this one down here has a stronger electrostatic attraction. Now, if you do decide you want to go into AP chemistry at some point, they don't prefer the word electrostatic, they prefer the word coulombic. Good Lord. So I'm just introducing that word to you. You don't need to know it this year. Okay, this is like AP Chem. They're all over that word. I don't know why. About 6 or 7 years ago, they decided they were all about the coulombic attraction, and they didn't want to use the word electrostatic anymore. But this is not important unless you're taking AP Chem. So if you're like, I am on the AP Chem road, you can learn that the word coulombic means the same thing as electrostatic force. Coulombic.
Is it a normal chem?
Huh?
Is it a normal chem?
No, not in regular chem. In regular chem, we still just call it electrostatic attraction because that's what most people call it. But like I said, for whatever reason, the college board that runs the AP exams, they get bugs in their ear about something or other, and then you're like, okay, I guess that's what we're calling it now. Now, if you're really into the depth of this, if you remember, we have our electron cloud here, and I'm going to color the electron cloud green. Sounds great. Okay, so here comes our electron cloud. I mean, it's colored gray in your book. You don't need to like color it, but I just thought it would be nice to see it. So that electron cloud, of course, is what charge? The electron cloud is negative. So we got little negatives all through there, right? Electrons, 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 electrons. Electron, 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 electron. Yes? What charge is the nucleus? The nucleus is... What particles are in the nucleus? Protons and neutrons. What charge are protons? Positive. And what charge are neutrons? Neutral. So what charge is the overall charge of the nucleus? Positive. Okay, so we got the nucleus, which is positive. We got the electron cloud, which is negative. We actually have both attraction and repulsion. Yeah? So the nucleus repels the nucleus. And we also have the electron cloud repels the electron cloud. However, to counteract that, we have the electron cloud attracts the nucleus of the neighboring atom. And we have the nucleus attracts the electron cloud. So in reality, you know, we give you these models that are really, really simple, but there's actually a balance between those charges and a balance between those forces. And where it is the most stable is how far they end up from one another. So there we are. Okay, this one is, I find this part a little bit more interesting than the whole, this one is a little bit like, oh my God, my brain is going to explode. There's attraction, there's repulsion, I don't know what's going on, whatever. This is much more concrete, okay? And I have some models that will actually show this. Okay, so first of all, do we remember what this is?
Salt.
That is a salt. And what's it made of? Chloride and sodium. And so what type of a compound is this? It's a square compound. What kind of compound makes these squares? Ionic compound form this crystal lattice, yes? What kind of bond is that? That's an ionic bond in between the positive ion and the negative ion. So this is an ionic compound. This is diamond. Ooh, don't steal it. Very valuable. Okay. Now, does anyone know what element diamond is made from? It's made from carbon. So each of these little black things is a carbon. And if carbon is attached to carbon, what kind of bond is that?
That's a
That's
covalent.
a covalent bond, okay? Because nonmetal to nonmetal is covalent. Are covalent bonds strong or are they weak?
Strong.
Covalent bonds are strong. Remember, anything that has the word bond in it is strong. The only thing that's weak are the intermolecular forces. Okay, so anything that says bond is strong. So these are strong bonds here. That's why diamond is so strong, because it's got these strong covalent bonds in between every atom. You can see like the ones in the middle, they're attached to 1, 2, 3, 4 other carbons. Okay, super strong, super regular structure. Can you have a big diamond?
Yes.
Can you have a small diamond?
Yes.
Is this a molecule?
No.
No. So sometimes, do you remember I said mostly covalent bonds form molecules? Sometimes you can get these great big, they call them covalent networks. And they're actually a form of crystal lattice. They're just a covalent crystal lattice, not an ionic crystal lattice. So these covalent network solids are actually covalent crystal lattices. But like I said, we also call them covalent network solids because there's a network of bonds in between each one. And the most common one that we come across and that we have a model of is diamond, just because it's easy to show. Okay? So here is diamond. You can see that little picture kind of looks like this. Yes? If you have silicon and oxygen, they also form a structure. You can see that's the basic structure. There's an oxygen with, or sorry, there's a silicon with 4 oxygens coming off, and then it sticks to other ones. You can also have, what is this one? Silicon carbide. I mean, you don't really need to know any of these particularly, but this last one is interesting because what does it look to be made of? It's all made of black atoms. That's made of carbon.
So is it made of the same material?
This is made of carbon, and this is made of carbon. This is diamond, shiny, goes in jewelry, harder than almost all substances on Earth. This is graphite. This is what is in your pencil. Okay, you can see how the different bonding structure makes it much more strong and less strong. And the reason is that when you have these carbons, the covalent bonds, do you see how this makes like a hexagon pattern? Okay. It is only these bonds in the hexagon that are covalent. Okay. How many layers do you see? 3 layers. These in between the layers, not covalent bonds. Okay, not covalent bonds. So what we have is we have a layer. So this would be layer number 1. Whoops.
What is it?
We'll get to it. Layer 2 and layer 3 and layer 4. So within the layer, it's all covalent bonds. In between the layers, we've got some weak forces. Can you guess what they might be? They are intermolecular forces between the layers. IMFs. Can we imagine that this is the tip of my pencil? Okay. And can we imagine that Max's desk is my piece of paper? Can we imagine that? Okay. And what I'm going to do is I'm going to now start writing on the piece of paper. Now, there will also be intermolecular forces between the layer of graphite and the paper. So what's going to happen is I'm going to come along and the paper is going to stick to that first layer by intermolecular forces. And it's going to, that pressing down, it's going to shear off. So this is actually, that layer is going to come off. And it's going to leave behind a layer of graphite. And that's how a pencil works, because these intermolecular forces get broken and we leave behind some number of layers of graphite. I don't know how many layers get left behind, but some number of layers get left behind. Yes? How does an eraser work? I think the eraser probably, I believe the eraser has stronger intermolecular forces with the graphite than the paper does. So when you rub the two together, that graphite layer is like, would I rather be with the paper or would I rather be with the eraser? And it says, ooh, eraser, more attractive. Yeah? And so it goes with the eraser, and then the little eraser fuzzies go all over the desk and make a big mess. It's always fun after my Chem 12 to write a test, and it's like, eraser fuzzies everywhere. Does that make sense? Cool. That was an excellent question, by the way. I love that. That was great. So here are our pictures of our atoms. All the atoms are bonded to all their neighbors by very strong covalent bonds. So this strong bonding makes the materials very strong and light, strong, and it should say hard here as well. Like diamond and quartz, which is silicon dioxide. And then this just talks about the graphite that we already talked about. This just shows it because here we have our strong covalent bonds. Within the layer. And we have weak IMFs between the layers. Okay. And that's it. I think. Do we have anything else after that? No. Yes, we do. Just a little bit. Yes.
Is there a way could we like turn graphite to diamond or diamond to graphite?
Yes.
Oh.
In order to turn graphite into diamond, you would have to put it under high pressure. Because what that's going to do is it's going to force the atoms to squish closer together. And when they squish closer together, you see how they're closer together here? Yeah. I don't know if there's a way to go backwards. I don't think there is. Okay? Yeah. Okay. Why are covalent networks always based on carbon or silicon? That's just something for you to think about. Have a little chat with your neighbor about that. Maybe draw a Bohr model of carbon. Group 14 has how many valence electrons? 4.
So that must be, oh, that makes sense actually. So they share all their electrons, so that makes it like really strong.
So, how many holes? 4 holes. So how many bonds? 4 bonds. That means that carbon can attach to 4 neighbors by covalent bonds, whereas oxygen, like if we just had oxygen and we were trying to have like oxygen form a thing, here's oxygen. 1, 2, 3, 4, 5, 6. It's only got 2 holes. Can you form much of a network when you can only bond on one side or the other side? Or can you just form a line? You can form a line, but you cannot form this 3-dimensional structure with things coming out in every direction. Okay? So it's the fact that they have 4 bonds. Are all substances based on carbon and silicon covalent networks? There's carbon dioxide. No. Is good? And I think is that it? Yes, that's it. So what you can do if you want to, if you're interested in doing this enriched part, you can finish the questions you didn't do yet on pages 55 and 56. Question. Do you want a quiz on covalent bonding on Monday? Do you know who's saying no? Do you know who's saying yes? The people who score well. Why are they saying yes? Why would they say yes? Because it's practice. I'll tell you what, I will make one. You can just actually, you know what, we're going to make it like we could make it like a practice quiz on Monday. And actually what we could do is I could give you the quiz and then we could go over it. You could mark your own. Does that make sense? So we're going to have a practice quiz on covalent bonding and molecules on Monday. Okay, so practice quiz. That's the best of both worlds, right? Because then you get the practice, but if you're like, I don't want to get the mark associated with it, you can be like, okay, that's fine. So practice quiz on covalent bonds on Monday. So number 1, finish 55 and 56. That is enriched. Number 2, there will be a practice quiz on covalent bonds on Monday, so study for that. That can be part of taking study notes. Yes? That's a very good question. Let me just see what I've got here. Here we are. Covalent bonding is pages 42 to 55, 56, 57. No, hang on. Oh, okay. Pages 42 to 65. There we go. That's for the practice quiz. So you've probably done a lot of it already. Okay, that's the sections. Okay. And then number 3, pages 75 to 80. Which you may or may not have done already. Yes, I know some people have. So, and number 1 is just enriched. So if you're like, I don't want to do that, you don't have to do number 1. You should be studying for your practice quiz on covalent bonds. And then 75 to 80, I know some people have already done it. If you've already done it, that's great. You just don't need to do it. Okay?
That's so irritating. Honestly, okay, so we have like student teachers in grade 7. It's not a religion. A lot of my friends are upset. Like, oh my god, he's so fine. That's me. He literally has a wedding. And no, like he actually is. Like she's like a good student, so like
43.
Shit. No, it's getting too far. He can't do anything. He's like really tiny. I didn't stop yet. Me either. You're already asking questions, bro.
Yes. Okay. Particle quiz.
You'll learn more about
My arms are like shaking. Number what? Molecule. I literally don't know the answer for this one. I just wrote my molecule. So like, why? I mean, I guess we'll have to. If you're the next step. Or you can look at the answer key. Yeah, but that's like. Wow, this one is kind of like better to. What properties is the same thing with all of this. I'll change it. If anything, it that's weird.
Oh, good, miss.
Yes.
Okay.
It is time for it to be the weekend.
Yes. Are you teachers allowed to go home early on Prodi days?
No.
Until 3.
Yes.
You should stay.
Yes.
Damn.
Hang on.
Okay.